So let's take a look at determining some of these angles for light that is reflected and light that is refracted. Super important slide. There's a lot of material on here. So let's start off by talking about what happens when a light is going to encounter some material. We have our old friend from chapter 32, the index of refraction, which is again the ratio of the speed of light in a vacuum to the speed of light in a material. Obviously it's going to slow down, and so this number will always be larger than 1. And we're going to be talking about angles of a ray that is incident upon some light. So we have the theta A, the angle of it relative to normal, relative to perpendicular in material A. That light wave is going to be first reflected back into material A, so we have our angle theta R. It's also going to penetrate and be refracted or bent into material B with angle theta B relative to the normal. Turns out that the angle that is reflected is just going to be equal to the angle of incidence, so theta R is simply going to be equal to theta A. For trying to figure out where the heck this light, or where the light ray goes in material B, we have to talk about what's called Snell's law, which is going to relate theta A and theta B. Turns out that it's related by the index of refraction, and we would say the index of refraction multiplied by the sine of theta A, that's going to be equal to the index of refraction in material B multiplied by the sine of the angle in material B. So that's kind of Snell's law right here. We could also write it as a ratio. Keep in mind that if you take a look at it like that, we have theta A right here, but this is going to be index of refraction of material B with index of refraction of material A right there. So super important equation. Make sure you're able to use this equation. Just kind of as a side note, if the wave is going to slow down, it's also going to change its wavelength. So the wavelength is going to be related to the index of refraction. Keep in mind that the frequency of material A must be equal to the frequency of material B. Because the wave is going to slow down, the wavelength must also correspondingly change. Since reflection is so easy, we're going to spend quite a bit of time talking about refraction. Something that is kind of interesting is the light of the refracted ray going to bend towards the normal or away from normal? Turns out that it's going to depend on the indices of refraction. So let's take an example of case A here, where we're going from a region of low index of refraction to a region of high index of refraction. Then light is going to tend to bend towards the normal. So we could also kind of say that theta B is going to be less than theta A. If we're going from a region of high index of refraction to a region of essentially a lower index of refraction, then the light's going to bend away from the normal or perpendicular line. So in this case we would say that theta B is going to be less than theta A. If it turns out that the ray is oriented along normal, then it's not going to bend regardless of index of refraction. So we can have a light that's going to be coming in like this. The light wave that's reflected back is going to be just in the backwards direction, and the refracted ray, regardless of index of refraction, is just going to be along the normal line. So if you have ever wondered why you're drawing a drinking glass or playing around in a pool, if you ever wonder why the object appears to bend at the water interface, this kind of talks as to why. Turns out that the index of refraction of water is going to be 1.3, and air is going to be roughly equal to 1. And so we're going to be going from a region of high index of refraction to a region of low index of refraction, and so light is going to tend to bend away from the normal. So we're going to have a light ray that's going to start at the ruler. It's going to go towards the surface of the water, then it's going to bend away from normal into our eye. However, our mind is trained to think of things as being in straight lines, and so it's going to view some apparent position of the ruler to be quite different than the actual position of the ruler. Just a quick little note, table 33.1 is going to give us the index of refraction for essentially yellow light. for a whole bunch of different surfaces or substances. So you might want to take a note that this is going to be table 33. Index of refraction is going to change slightly with wavelength, but we don't particularly care about that in this class. So let's take a quick look at example 33.1, which is going to be asking, where is this light ray going to go? And we've kind of ignored the easy interface, which is going to be the interface from air down to water, and we're going to be looking at the interface from the water to the glass. We have light that's incident at an angle of 60 degrees, and we're going to say, well, what is the angle of reflection? What is the angle of refraction? Well, the angle of reflection is quite easy. It's just going to be 60 degrees. For this angle right here, theta b, we're going to say we need to apply Snell's law, and I've already written it to save me a little bit of time. And we're interested in this angle theta b, so let's first go ahead and divide both sides by the index of refraction. And then we can say, well, I'm interested in theta b, so I need to take the arc sine. So theta b is going to be equal to the arc sine of this beast right here. Index of refraction A is going to be index of refraction of water, 1.33. Index of refraction B is going to be 1.52, and this is simply going to be the sine of 60 degrees. You go ahead and you find out this angle is going to be simply 49 degrees. Make sure you're quite comfortable with applying Snell's law. Now, one interesting concept is that of total internal reflection. This type of reflection is only going to occur when we're going from low index of refraction to a region of high index of refraction. So we know that if we go from low to high, that the angle is going to bend more away towards the normal, or more away from the normal. So if we consider a case right here where we have a light wave going in that direction right there, it's not going to be bent at all. Light wave number 2 is going to be bent away from the normal. Light ray number 3 is going to be bent at exactly 90 degrees, and light ray number 4 is going to be at such an angle that it cannot be refracted. It will be bounced backwards, back into the material. This angle is called the critical angle, and the light undergoes what we call total internal reflection. Now, Snell's law is going to boil down to tell us what this critical angle is. It's going to depend on the index of refraction of the two objects, NB divided by NA. And this is something that you've probably experienced if you're playing around in a pool looking upwards. You're going to see there's some angle with which you can't see outside of the pool. We can kind of take a look at it for two laser beams that are going down into a glass bowl right here. They're going to bounce off of mirrors and get reflected off at two very close angles. However, this one right here is less than the critical angle. This one is greater than the critical angle, and so it's going to be bounced back down towards the water. Some applications of total internal reflection is going to be something called prisms, which I don't know a whole lot about, but also going to be fiber optics, which I do know a lot about. For a fiber optic, it's essentially a piece of glass that you can shine light through, and it can bend the light ray. So here we have a light ray that's coming into this piece of glass, and it undergoes total internal reflection at that angle, and that angle. And this is actually very useful for optical design, because you can you don't have to have straight paths for your light to travel in. So very, very useful application in real life. And of course, another application of total internal reflection is going to be why are diamonds so sparkly? Well, it turns out that they're cut such that there is total internal reflection on their back surfaces, and all the light's going to reflect off the back surface and shine out of the front surfaces, giving you a little bit of shine on your finger. Another concept that has to do with refraction is this idea of dispersion, and essentially I made the remark earlier that you don't care that the index of refraction depends on wavelength. I was thinking strictly of a problem sense. It turns out that the index of refraction does actually depend on wavelength, so it's a function of wavelength, and for different materials it's going to change slightly differently. For something like fluorite or fused quartz, the index of refraction right here is going to change just a tiny little bit over the spectrum of light that we can see. However, if we wanted to take a look at something like silicate flint glass, you can kind of see that the index of refraction is going to be 1.625 right here, and it's going to be closer, or 1.675 right there, and closer to 1.625 right there. You can also kind of see that the index of refraction is always going to be higher at the blue end of the spectrum compared to the red end of the spectrum. Now, having different indices of refraction, what that means is when white light is going to be incident upon a surface, then that light is going to be bent at different angles using Snell's law. Because blue always has the larger index of refraction, it's always going to be bent more away from the normal. So light's going to come in, and it's going to bend that interface, and the red light is going to bend less, the blue light's going to bend more, and then there's going to be another interface, in which case the blue light is going to bend more, and the red light is going to bend less. And so we can get kind of a rainbow coming out of a prism, kind of a cool little concept. Dispersion also leads to us being able to see beautiful atmospheric phenomena such as rainbows. And essentially, a rainbow is going to be a combined effect of dispersion, refraction, and reflection. If we consider some light rays kind of coming in from the sun, and we're going to kind of number those guys to keep track of them, these guys are going to enter kind of the raindrop right here, and we'll assume that it's spherical even though it's not. And these guys are going to all bend, and they're going to hit different parts of the back end. Some will be reflected, some will be refracted, some will leave the raindrop, and they're all going to kind of come out at different angles right here. Kind of a nice little mess here. Now suppose we have an observer, and that observer is going to be right here looking at this raindrop. He's only going to see the light ray that's coming from 6. And what that means is, let's just say 6 is going to correspond to a certain color, and let's just say that color is red. Now there's going to be presumably another raindrop just below this guy. It's going to have the same kind of thing where light's going to come in a parallel sense, it's going to bounce around, and one of the light rays is going to bounce back and reach this guy. It's going to be a different color. Could just say that this could be the color of yellow, and kind of so on and so forth through all the other colors. So what this really means is when you're taking a look at a rainbow, you're seeing the light that's reflected from several different raindrops that all correspond to several different colors, and it turns out that these guys are going to kind of form an arc for each color. This also means that each rainbow is going to be unique. An observer over here, say, is going to see a totally different rainbow, so no two rainbows are going to be the same. Now the angles do sort of matter. The sun has to be at just the right angle from you, maybe in the 40 to 42.5 range, and again, each raindrop is going to send just a certain color into each eye, and it's going to be several raindrops that make up the full spectrum of light that you're going to see. Now what about that elusive secondary rainbow? That rainbow is going to undergo 2 internal reflections, and you can kind of see right here what's going on. It's going to have an internal reflection there and there. The light's going to disperse, but because there's 2 internal reflections, note that here the colors are going to be reversed, and you can kind of see in this picture right there that this goes from red to blue. This one's going to go from blue to red. So that kind of explains why there's why the colors are reversed, is because it undergoes 2 reflections.